Okay, so in our last video we looked at Sn1 versus Sn2 and just trying to make how to make decisions about which substitution mechanism happens. Let's take a look at some unusual cases here. So when we look at Sn2, what I said in the last video, which is usually true. Sn2, we say this never, actually let's look at Sn1. We say Sn1 never happens for a primary electrophile. And that's not totally true. There are two cases where it does happen. So remember, the real rule here has nothing to do with primary, secondary, tertiary. It has to do with the stability of the carbocation. How stable is the carbocation that's going to form? And so the reason that it works out that a tertiary is more reactive in an Sn1 reaction is because tertiary carbocations are more stable. But the substitution on a carbon is not the only way to stabilize a carbocation. Another way is through resonance. And so if you've got a primary substrate, which is what this is, but it has a leaving group in the allylic position, which is where this bromide is, now you've got a situation where it could go through Sn1. So this can come off and form a stable enough carbocation. We can draw out the resonance structure for that. That it can go through an Sn1 mechanism. So for allylic primary for electrophiles that are allylic, even if they're primary, they can still potentially go through Sn1. And so this is a case, again, where in the last one we saw this for secondary. If I try and use a nucleophile that's good, this will go through Sn2. But if I use a nucleophile that's bad, so for example, if I use, let's say, acetic acid, this is going to go through Sn1. So it can go through either. Oops. And so this is why it's important to kind of understand these things at a fundamental level. Because the tertiary, secondary, kind of memorizing the order there only gets you so far. You'll note that this thing can still go through Sn2, and that's because Sn2 is always favorable when there's no sterics involved. So if the steric hindrance is low for the nucleophile and it's low for the electrophile, then Sn2 can happen. And just because there's an allele near there doesn't really change the steric situation very much. So Sn2 is still favorable. But now what's happened is, so that's kind of what you would expect, but now because of the stabilization of the carbocation that can happen, we can also go through an Sn1 mechanism. So that's the allylic position, and we've kind of learned about that already. Be careful that you don't confuse allylic with vinylic. So remember the vinyl position is right here. This one we just don't see go through anything. Doesn't go through any kind of, if you try and react this with a nucleophile, we just don't really get any kind of, let's say, how would I put that? Let's say, doesn't, not reactive to Sn2 or Sn1. So yeah, so the leaving group has to be on an sp3 hybridized carbon. If it's on a carbon that is, if it's on a carbon that's Sn2, that's sp2, as it is here, we just generally don't see any kind of reaction happen there. Okay, so all of these reactions that we're talking about are strictly for things that are attached to sp3 hybridized carbons. In other words, just things that are not attached directly to a double bond or a triple bond. Allylic, in these situations where things are allylic, this isn't directly attached to that double bond. It's attached to a carbon that's attached to the double bond. So that can be a little bit confusing when you first get started. Another group that you'll see is called the Benzylic group. So Benzylic groups are like allylic groups. So if you want to draw the comparison, right? This portion of this benzyl group looks the same. Oops, sorry, that's the wrong one. This portion of the benzylic group looks more or less the same as this allylic part. It's just got this other part of the ring that's happening over here. So it's sort of like an allylic situation, but it's kind of even more favorable, or you can think of it as being more favorable, because once this pops off, okay, yeah, it's a primary carbocation, but I can form all these nice resonance structures with it. I can push this around the ring. And draw several other resonance structures for it. This, I think, is the last one, at least the last major one. Okay. So benzylic carbocations can also undergo Sn1. I'm sorry, primary benzylic electrophiles can also go through Sn1, and they can also go through Sn2. So you have to look at the nucleophile, just like we did in the last question, to figure out whether it's going to go one or the other. Okay. So yeah, keep an eye out for those. And let's take a look. Let's see. Let's take a look now. Let's take a look at what's going on, really, when we think about what's happening in the flask. Okay, so if we've got, let's say we're just dealing with the normal. Actually, let's make it interesting. Let's take something and it's got some stereochemistry to it. So I'll put a bromide on there, and we'll put a CH3 group here. Make this an ethyl group, and then we'll put our hydrogen towards the back. Okay? Let's see what can happen. So let's say I add in a bad nucleophile. Let's say we use water. We can consider two different paths for this. So we're saying these things are in competition. So conceivably, if we waited long enough, you could see either Sn1 or Sn2. And we can kind of consider what's going on here as far as why one happens versus the other. So for a bad nucleophile, we've got water. So let's look at the Sn1 path. So in the Sn1 path, our first step, really this is reversible, is to lose the bromide and form a carbocation. Okay. And then water comes in and attacks that position. And remember, it can attack from either side, so what we end up seeing is the one that we get from the attack that I've drawn. And we would also see the one when we attack from the top. So we'd see a racemic mixture. And then in the final step, which not going to draw out, we would lose the proton. So we would end up with a racemic mixture. Actually, I can draw that out. There's no reason for me not to. Yeah, in our final step, what do we see? This proton goes back into solution. And we end up with a racemic mixture. So we'd get this. And then we would also deprotonate the other one. And you can convince yourself that these are actually enantiomers if you want to refresh your knowledge of stereochemistry. So that's what happens during the Sn1 pathway. Yeah, so why not Sn2 just because the nucleophile is bad? Okay, so in the Sn2 reaction, what would happen? Sn2 reaction, what would happen is in the first step, the water would have to come in and attack there at the carbon and kick the leaving group out. I'm going to highlight the arrows for the Sn2 pathway in pink here. Don't confuse those with the Sn1 pathway. Let's say the Sn1 pathway I'll do over here, and we'll put that color as about dark purple. Okay, so that leads us down this path. Takes us down this path. Now we're looking at what happens if we do Sn1. And so the electrons from the water come out and they would kick that off. And so what we would see is, in this particular reaction that I'm showing you, you're starting with something that's enantiomerically pure. I've only showed you one enantiomer for it. And so you would see an inversion of stereochemistry. Yeah, maybe this would also be reversible, sure. And then you would get deprotonation. So in reality, both of these mechanisms would be in competition with one another at the same time. They'd both be happening simultaneously in the flask. It's just that one of them is going to happen much faster than the other. And we know in this particular case, because we kind of already looked at something similar, that the Sn1 is the predominant mechanism. And if you wanted to know, like if you were just trying to looking in the lab, like you were doing this reaction, one way that you could look at that and know if it was Sn1 or Sn2 would be to check the stereochemistry of the product. So if I looked at the stereochemistry of the product and it was racemic, very close to racemic, then I would say this thing's predominantly going Sn1, excuse me. And if I saw inversion, then I would know that it was going predominantly Sn2. Okay? But we know even before we run this experiment in the lab, because people have studied this, that this goes predominantly through Sn1. So let's take a look and see why that is. Why is that true? Because both of these look reasonable. They're both reasonable mechanisms. So Sn1 is generally going to be pretty is generally going to be a pretty slow process. And the reason is that the activation energy to form, let me get what did I use this one? The activation energy to form this carbocation is really high. This is a high energy species, right? It's difficult in general, and this is again, you can relate this back to Hammond's postulate, but it's difficult in general to form things that are high energy species because the barrier to getting to those species is going to be very high as well. And so in order for it to have a chance of forming, the energy barrier has to be lowered, and we've done that because it's secondary. But how does it outcompete the Sn2 reaction? Because the Sn2 reaction on the other side, this reaction, it doesn't even form a carbocation, right? You'd think this would just inherently be a faster route no matter what. And this is where the bad nucleophile thing comes in. So because water is such a bad nucleophile, the rate of Sn2 turns out to be much slower. So I hate to haunt you guys with stuff that you should know from general chemistry. But remember that the rate of this reaction is dependent on K times the concentration of water times, I'm just going to call it in this case the substrate because I can't abbreviate that very easily. Or, you know, the electrophile. Maybe electrophile sounds better. And over here, we just know that the rate for Sn1, that one's just going to be equal to K times the electrophile. Okay. So these K's between these two, I'll call this K, if I can write that small, we'll call this K Sn1, and we'll call this K Sn2. So those rate constants are different for Sn1 and Sn2. So what ends up happening here, because water is such a bad nucleophile, K is small. So K Sn2 is small because water is a terrible nucleophile. So the effect of the changing the nucleophile has a big effect on the Sn2 reaction because, you know, it's part of the rate determining step. And in this situation, the rate constant becomes really small. But changing the nucleophile doesn't have any effect on the rate determining step for Sn1. So we haven't sped up the Sn1 reaction to make it more competitive. We've sort of just hobbled the Sn2 reaction, right? So K-Sn1 here is the same regardless of what the nucleophile is because the nucleophile doesn't appear in the rate determining step. And so by taking a nucleophile and just making it a bad nucleophile, you can slow the Sn2 reaction down. And that essentially gives the Sn1 reaction a chance to win this sort of competition. So the comparison here, so Sn1 reactions are generally pretty slow, okay? So Sn1, what I'm trying to say is Sn1 is generally these are slow. And Sn2 is generally pretty fast. But when we have Sn1 winning, so in order for this to win, let me see if I can say that a different way. Let's say Sn1 is generally slow. Let's just leave it at that to start. Sn1 is generally slow. In order for it to win, the competition with Sn2, it can't become faster. Sn2 must become slower. So it's kind of like, if I were to go and try and race Usain Bolt, right? There's no way that I could ever get fast enough and train hard enough to beat Usain Bolt. Even though he's retired now, I still don't think I'd have much of a shot. My only shot at beating Usain Bolt would be to make him slower, right? So I'd have to hire somebody to go and break Usain Bolt's leg so that I could beat him in a race. And that's kind of what we're doing here when Sn1 is outcompeting Sn2. It's not because the Sn1 reaction is getting faster. The Sn1 reaction is staying the same speed, okay? It's that the Sn2 reaction is getting slower. we've essentially broken one of Sn2's legs because we've taken the nucleophile and made it really crappy. And this makes the rate constant really small, and then now Sn1 can compete. So Sn1 it's a slow racer. It's the Dr. Dragna in the race against Usain Bolt. But Dr. Dragna has friends that can break Usain Bolt's leg, or in this situation for the Sn2 reaction, just put in a bad nucleophile. And that allows the Sn1 to win. Okay, so Sn1s are always slow, but if we can slow an Sn2 reaction down enough, we can start to see the Sn1 start to compete. And that's what we're seeing in these reactions where you have a secondary substrate. How is Sn1 winning at all? Well, because we've slowed Sn2 down enough by making the nucleophile bad. If you look at the tertiary situation, so we consider the tertiary situation, let's just make this one a little bit simpler. Get rid of the stereochemistry, because I think hopefully the general aspect of that sticks. Okay, again, this is going to be very slow to happen. Oops. Just because carbocations generally don't like to form. They're very high energy species. So this is going to take a while. But in this case, we hobble the Sn2. We slow the Sn2 down because there's so much steric bulk. If we look at the steric hindrance here, there's all this steric bulk here. So even if I introduce a really good nucleophile, maybe cyanide would have a shot at doing Sn2. I don't know. For us, we're going to say no. Let's say I put in cyanide. So now I haven't hobbled the nucleophile. This is a good nucleophile. This is still going to be too slow to just form in one step. Okay. This is still slower. So this one's slow because of sterics on the electrophile. But in all of these cases, you'll notice that the Sn1 speed always the same speed. Just same. I don't know how to say it. It's just like generally it's just going to be the same. So I can change things. Maybe the Sn1 will be a little bit faster because this is tertiary. But generally just Sn1 is really slow. But if you can slow down the Sn2 enough, then the Sn1 can win. And so in the tertiary case, it's just that the steric hindrance around the sigma star orbital, that's kind of on this backside over here that we look at, right? It's just really hard for even for cyanide, which is a very small nucleophile, to get in there. So the probability of it actually being able to hit that the little orbital that's nestled in between the methyl groups there is very small. So the rate of reaction is very small for Sn2. But the Sn1 is whatever. It just stays the same, so it doesn't change anything. So now in this case, the rate constant is smaller because of the electrophile. Up here at the top, right, our rate constant was smaller because of the nucleophile. And that's really all you're looking at usually. When you're comparing Sn2 and Sn1, you're saying, is the Sn2 going to be slowed down enough to allow the Sn1 to happen? And there's two things that can happen to do that. One is we can make the nucleophile really crappy. The other is we can make the electrophile like really sterically hindered. And then in the ideal case, the thing that's fastest for an Sn1 reaction is to take something that's tertiary. So I've slowed Sn2 down a good bit with that. And then in addition to it being tertiary, I use water or some other really bad nucleophile. So I even further slow down the Sn2 reaction. And now the Sn1 really has a chance because the Sn2 reaction is going to be significantly slower. Okay, so you can see how these sort of things all add up to allow you to have Sn2 versus Sn1. And really what you're looking at, when you look at these flowcharts and things, it makes it seem like, it's just a way to solve problems, but it doesn't actually give you much insight into what's going on chemically. What you're really trying to compare are the rates of reactions between these things. So given an infinite amount of time, one of these mechanisms will always take place for a substitution reaction. It's just a question of which one. And for Sn2 versus Sn1, all you're really looking at, you're never really changing much about the rate of reaction for Sn1. You're just changing the rate of reaction for Sn2. You're seeing, can I slow Sn2 down enough to allow Sn1 to have a shot? So, yeah, it gets complicated when you actually start to look deeper into it, but, of course it's complicated. We're looking at atoms and stuff. So I'd say that the levels of learning in terms of comparing these two things is, can I use a set of heuristics like a computer would and just say, is it tertiary? Is it a bad nucleophile? If yes, then probably Sn1. If no, maybe Sn2, that kind of stuff. Or you can actually kind of take your time and sort of try to parse out the physical organic chemistry here and understand it in kind of a deeper level. And probably like learn it in a real way. I think that kind of just depends on you. I'm not. It's going to be challenging for me to kind of test this stuff in the quizzes, but I'll probably find a good way. At the very least, the lowest bar is just be able to look at a molecule, look at the nucleophile, and say, is it going to happen via Sn1 or Sn2, right?